Nam Phương Việt, tạo dựng niềm tin.
Motion control into tier portal, as well as the new SINAMICS V90 drive. In this video, we will be looking at tuning. The topics covered are listed on screen. To access the control panel for our drive, we go to Ungroup Devices, select the drive, and select Commissioning. To take control of the drive, we must first go online. Once online, we can activate master control from the control panel. Now we have control of the drive, we can switch it on. This will change the ready light on the front of the V90 to green. If we give it a speed set point and press forward in continuous operating mode, the drive will run. Jog Control is also available within the drive's control panel, along with the actual values for speed, current, torque, and thermal utilization. To begin speed loop tuning, we go to the optimization pane. If we select further values, we can see all the factors that will be tuned. These will be different depending on the dynamic factor we have selected for our tune, which defines the responsiveness of the axis. When performing an automatic optimization, the axis may need to move up to positive and negative 720 degrees and in an erratic fashion, so caution should be taken. If the axis needs to move further than the maximum angle of rotation you have specified, an alarm will be caused and only a partial tune will have been performed. At present, the values are only held in the online RAM memory of the drive, so we must perform a RAM to ROM in order to retain the values after a power cycle. We also need to upload the values from the drive so they are saved in our project. To find the Technology Object control panel, we identify our technology object and select Commissioning. Like with the drive control panel, we activate master control and accept the monitoring time message. From the Technology Object control panel, we can manually control the positioning loop. We are offered more options than in the drive control panel, such as acceleration, deceleration, and jerk, as well as having many more operating modes, such as homing or positioning relative. When leaving the control panel, we must disable the axis and deactivate master control. To begin tuning, we select it from the list and activate it in the same way as we did the control panels. Firstly, we need to configure our measuring parameters: distance moved, acceleration, maximum velocity, and measurement duration. We are going to use the dynamic default values set in our technology object. The tuning pane will notify you if the values you have selected will not perform a meaningful measurement by highlighting the field in orange. To start tuning the gain, we completely remove pre-control so we can more clearly see the effect. We will first do a control measurement of the default value for gain. Scrolling down, we find a small trace window which by default will plot target position, actual position, target velocity, and actual velocity. To start with, only the position and actual position are visible, so we enable the velocity and actual velocity, and then change the scaling groups to overlay the graphs on top of one another. We can see that at the moment our velocity has quite a sluggish response, and so we're going to increase the gain to try and improve this. As we can see, the gaps between the graph lines have become much closer together. This gap is known as following error. Reduction in following error improves the dynamic performance of the drive. We're going to increase the gain again to see if we can reduce it further. We now have a much more dynamic response than our first trace. If we select the magnifier tool, we can zoom in on parts of the graph to get a closer look. As we can see, there is still a fair amount of following error. We can now start tuning pre-control. Pre-control allows the interpolator to feed set points forward to the speed controller. This allows following error to be massively reduced with essentially predicting the set points ahead of time. However, it is heavily reliant on a high dynamic system. If the system contains, for example, mechanical stiffness, uneven loads, or high inertia, which the pre-control cannot account for, then it must be set much lower as more feedback measurements are required to accurately control the system's movement. Pre-control is defined as a percentage of the speed set point which can be fed forward from the interpolator. As this application has a very low inertia motor and very little load on the end of the motor, we can increase pre-control all the way up to 100% and get a very dynamic response. It should be noted that due to our application, the values seen here are very high. In a real-world application, you're more likely to see much lower values than this, unless the system is extremely dynamic. At 100% pre-control, we have just started to overshoot. This is usually an indication that the drive is at its limit of tuning. It should be noted that when you perform a tuning measurement, the trace is stored in the traces section of the controller and can be retrieved at any time.